Hi, welcome to this video where I want to do again a sample calculation, and in this case I would like to talk about stopping time of water droplets in air. So if we look what's the idea for this video, we first look at a simple example which considers a single particle in gas, and then we repeat the force balance for this case, and finally we will calculate the solution for the given task in this video. So generally, we talked in the previous videos a lot about how particles move in gas, and one really fundamental case in this topic is the motion, the transient deceleration, so the stopping over time of a particle moving through a gas. This is a very important question in a lot of unit operations, and therefore I would highlight this with a small sample calculation. So the question here, and this is basically from the previous video, right? So calculate the time and the distance needed to stop a 50 micron and a 500 micron water droplet from a starting velocity of 20 meters per second in air. So we have a water droplet in air, and the question is how fast and will it stop, and what is the time, what is the distance it travels during this time. And we look at a smaller and a larger particle, and then I also ask you to play around a little bit with the particle size and also with the velocity. Here we will just look on particle size to get a little bit an idea of these variables or properties. So if we look at this case, we first need again the force balance, and the force balance of a particle in gas was quite simple. We just considered a drag force, so Stokes regime, because mainly the particles are very small, and small particles means small Reynolds number, and this means Stokes regime. So the particle moves, and when it moves in one dimension there is a drag against it, and the drag decelerates the particle, so it slows down. So we also have an inertial force, and these are the two forces which have to be considered. And if we make the force balance with these two forces, we will end up with the final equation, which was derived in the previous video. And this equation is the velocity depending on the time, or velocity as with time as a variable. Then we have is depending on the starting velocity and of course the variable, and the t star, and t star is the relaxation time or also characteristic time, and this is basically the density of the particle, the size of the particle, and here we also have the influence of the particle because it goes to the square, and then we have also the viscosity of the fluid around, which is air, so gas velocity, viscosity in this case. So this is basically the equation we have to solve with the numbers we have. So with a 50 micron particle size and with a starting velocity of 20 meters per second. And with this we would first calculate the relaxation time. So if I wanted to see the stopping time, what is the time the particle needs to reach zero velocity, I first calculate the relaxation time t star, and the density is given for air. And then we also have the density of the particle. The density of the particle for water, 1000 kilogram per cubic meter. I was confused because of the large number for one time. And then we have the size of the particle, which is 50 microns, so 50 times 10 to the power minus 6. This is squared. And then we have 18, and then we have 18 because times the viscosity, dynamic viscosity of air is 18 times 10 to the power minus 6. So 18 multiplied by 18, 10 to the power minus 6. And if we make the math, we will get a characteristic or a relaxation time of 0.0077 seconds. And this can be now put into the equation, right? And if we look again at the equation, the question was, what is the time we need, t, to reach zero velocity? But if we look at the equation, so we would want to have 0 here, so we get 0 on left part of the equation, and if we want to get rid of this e, we need the logarithm, and the logarithm is for 0 not defined. So we have a problem here with solving this, and this problem can easily be treated by saying, yeah, maybe we just need to reach 1% of the starting velocity, because 1% is very close to 0. So in this case, we say, what is the time to need only 1% of starting velocity? So this means that the final value I would like to calculate is 0.01 times the starting velocity, so 1% of the starting velocity. And if I put this expression in here, I will have 0.11 multiplied with V0, and we have a V0 here, right? So if I divide it by V0, this goes away, and V0 here goes away. So I have 0.01 equals, and now I have just this term, and T star is known. So e to the power minus t divided by 0.0077, and now if I take the logarithm and multiply with 0.0077 and get rid of the minus, I will end up with a time of 0.035 seconds. So a 50 micron droplet, water droplet in air, having a high starting velocity of 20 meter per second, stops within 0.035 seconds. So this is extremely fast, okay? And now we can take a look, what is the distance the droplet travels during this 0.035 seconds, which is probably not very much, even if the starting velocity is high. And therefore we derived this equation in the last video. So this is the distance traveled over time, depending on the starting velocity, the relaxation time, and then we have 1 minus e to the power minus t divided by t star, and we have all the numbers, or everything is known, so we just can put all the numbers in: starting velocity, relaxation time, and the stopping time was also calculated. So this will end up with 0.15 meters. So this is, for the very short time, a decent distance, right? It's 150 millimeters, but the droplet is also very fast. So even if the short is very short, it still travels a certain time. So now let's take a look at a larger droplet. And if we increase the time by the power 1 digit, so we take now 500 micrometer water droplet. We first calculate the relaxation time, right? Nothing changes, just here 0 appears more, and then we get 0.77 seconds as the relaxation time. And if we now calculate for 1% of the starting velocity, we will end up in 3.5 seconds. So a 500 micron droplet now needs 3.5 seconds, and this is observable, right? 1, 2, 3.5. But this is a time scale which is observable. And if we look at the distance, so in this time the droplet nearly travels 20 meter per second. So nearly 1 second of starting velocity, because it decelerates in this time, right? But this is a very long distance compared what we saw before for the small droplet. And now we can play around a little bit with the numbers, and if you put everything into a Python code, so we have the stopping time between 1 and 1000 micrometer. So here's the stopping time, and here's the droplet diameter in micrometer, and you see the axes are log scaled, and this is because of the power law relation. So the stopping time depends on the particle size squared, and this is if we go over this large area from 1 to 1000 micrometer, we need a log scale, and this is a straight line with a slope of 2, and the slope of 2 clearly says, okay, the relation is to the power of 2, because this is the idea of the power law, right? And this means that a small droplet, so if we consider Stokes regime, so only viscous drag, a small droplet stops right away, right? So a small droplet within 0.00 seconds stop. So we don't really need to consider stopping time or distance for small droplets. But since this depends on the squared particle size, with increasing droplet size, these large droplets can travel a quite decent distance. And this is extremely important in aerosol technology and spray technologies and so on. So if we take a look now at the distance, so we have the stopping distance over diameter, and then we will see the same picture, right? For small droplets, the distance is extremely short, but for larger droplets, the distance goes to 1 meter, even to 10 meter, as we saw in our example. So with this, I would like to repeat. So we look at a simple example considered a particle in gas, right? So we looked at the water droplets of 50 microns and 500 microns and want to understand the stopping distance and the stopping time. And therefore we repeated very short the force balance and looked at the final equation. And then we calculate with the equation to solve the task and looked also at the result of a Python code. So with this, I really would like to thank you for watching the video, and if you have any questions, please let me know.